All right. So thanks for coming today. I would like to introduce Allison Baker. She got her PhD in the applied math program here. She did a bunch of work on solvers, iterative solvers, multi-grid methods, things like that. At that time and in her work at Livermore. So she was at Lawrence Livermore National Lab and then moved to NCAR in 2012. And I sort of transitioned into more like data intensive work. So looking at compression techniques and sort of how to work with these multi-physics simulations. So she's working on the community Earth system model. Very large group of people. It's a very interesting dynamical system in which determining are we making good predictions or are these correct answers or did this code change really affect correctness are very challenging problems. And that's what she's going to talk about today. So thank you.
Thank you, Jed. Am I good with the microphone? It sounds like it. Okay. Yeah, so this is work that I've been doing for several years with a number of collaborators. My main collaborator is Dorit Hammerling. She's a statistician who was at NCAR and now is at Colorado School of Mines. I think the acronym for that is CSM, but now I'm not really sure. You might recognize Dan Milroy's name up there. He worked with Dorit and I and Liz on his PhD, and he graduated in December, and he's out at Livermore now. So some of the things I'll talk about are things that where Dan was really involved in. So probably, hopefully you guys all have taken the time to look up the hill, seen NCAR. I work up on the 4th floor in one of the towers. It's pretty cool. Hopefully you've at least been hiking there. We're funded by the National Science Foundation, and I forget how many people work there, but there's a lot of people doing climate, a lot of people doing weather, doing space weather. It's a pretty fun place to work. Our computer is not in Boulder, it's actually up in Cheyenne, Wyoming. So if you're ever up in Cheyenne and start taking I-80 and you sort of look north, after about a couple miles, you'll see this huge parking lot full of like more Walmart trucks than you thought you'd ever see. And when you see that, you just look a little farther, and that's our building. And it's, you know, the computer is a computer, but the building has won lots of awards for like green design and stuff. It's a pretty cool building. If you're ever, you know, up there and it gets really windy and you want to go inside. So, let me talk a little bit about what a climate model is or what an Earth system model is. So these models are really complex. They are trying to couple together, you know, the stuff that's going on in the atmosphere, things that are going on in the ocean, on the land, how everything interacts together. They're super useful, especially now that, you know, there's increased focus on our climate and we're wanting to answer all these what-if questions like, what if all the ice in the Arctic melts, hypothetically? What's going to happen? So they're really great tools for that. There's a lot of different climate models around the world. I would say this is one of the most commonly used. We have about 8,000 registered users. And even though the development has been led out of NCAR, this is really a community project. And we have lots of university collaborators, Department of Energy collaborators, and just people from all over working on this code. And the first kind of climate model code at NCAR actually started in 1983, and that was just modeling the atmosphere. It was like another decade before they coupled in the ocean. So yeah, so the CESM, the Earth system model, there's lots going on. We have all these physical equations that are, you know, doing the fluid motion and radiation, and there's lots of chemical things going on. We've got a 3D grid. The grid can be different for the ocean, for the atmosphere. It can be a different type of grid. I have a few types up here, different resolutions. There's a lot of things that are happening that we're trying to model that happen at a scale that's smaller than the grid. So like to model a cloud, you need to be down more like around a kilometer, and you'll see that these models are typically run at more like 25 to 100 kilometers. So things that happen at a smaller scale than the grid, we parameterize, which means we basically approximate them somehow. And the code itself is actually written so that all these components are separate. Like there's a separate group of people working on the atmosphere, the land. These are all individual components that can be run on their own. And then they're all coupled together through the appropriately named coupler that brings everything together. We can switch out different components, like we might be using one ocean component for one experiment and another one we want to use something simpler, so we can switch it out. So basically, there's a lot going on. And a lot going on means we have nearly 2 million lines of code in the code base, which is a lot. But this is, 20 plus years in the making. It is in Fortran, which is exciting. Some of it is cool, modern Fortran, and some of it is old, embarrassing Fortran. And there's a nice, healthy mix. There's lots of functions, lots of subroutines. You can run it on your laptop. You can do a really low resolution, run something on your laptop. We've recently run on the cloud using the Amazon Web Services. High resolution, you have to use a supercomputer. And so my basic point with this slide is that there's a ton of code, there's a ton of people working on it, it's changing all the time, and somehow we have to make sure that everything is good. And this is just some eye candy I put up here. This is a high resolution run. We have the sea surface temperature and water vapor, and when I say high resolution, that's like 25 kilometers in the atmosphere. The ocean, they go a little finer, and those are expensive. Those are like 250,000 core hours to simulate a year of climate. So usually, like if someone gets can simulate 2 to 5 years in a day, then they're happy. So if you want to run 100 years, that's a long process. More a baseline is 1 degree, and by degree I mean like latitude and longitude degrees. So a degree is about 110 kilometers. And so when I refer to baseline runs later, I'll be talking about 1 degree because the high resolution are expensive. So we've got all this code, all these people working on it, all this stuff going on, and at the same time people are using the code to maybe make predictions about the future and how society might respond to something. So we want to make sure people have confidence in the code, and so that's kind of the whole motivation for this project, is that with everything going on, we have to make sure we're not doing something bad to the code, that we're controlling the quality. And this really, the motivation for this particular work came from, we're frequently porting the code to different machines. So, we have our machine at NCAR, but they run it at Argonne and Livermore and NERSC and universities and CU. And so we needed a way to make sure, well, when they port the code and we don't get the same answer, is it okay? So it's really easy to tell that your code is correct or the same as the old code if you get the exact same answer. And you can get the same answer with CSM. It is deterministic if you use like the exact same software and the same flags and the same initial conditions, and it's Tuesday morning and you had oatmeal for breakfast and everything is the same, you can get the same. But that just doesn't happen because it's real life. And requiring that things are bit for bit is really restrictive. And so the last several years, we've really been able to get the climate scientists to kind of let go of like, it has to be bit for bit or it's not right. And this is really important because this is a lot of code and it takes a lot of time. And so we need to do things like optimize and use O3 instead of O2 and take advantage of new hardware and stuff like that. So we need to be able to do things that are not going to result in bit for bit answers, but we can still say, no, we feel good about this. So this is, I just wrote it, well, not too formally, a little more formally because I put the yellow box. So let's say we run our data on the machine at NCAR, and then we port the code to the machine here at CU Summit, is that right? And so now we run on Summit. We do the same setup, but of course the answer isn't the same. And so we're wondering, all right, so the answer's not the same, but is it still correct? I mean, does it still represent the same climate, or was there some bug in the port? I mean, should I panic like this little guy in the corner? Hopefully not. So the idea is that we need to assess, what is the difference between the output on the two machines. And the thing that's hard about that is, if you talk to the climate scientists, they're like, well, we just want to, reach the same scientific conclusion when we look at this other data. I mean, we don't want it to be climate changing. And I'm like, well, what does that mean? Well, yeah, there's not an answer for what that means, really. So in the past, what they did is they would run like several 400-year simulations on the NCAR machine. Then they would run several 400-year simulations on Summit. And then someone with climate expertise would actually look at the data and give it the thumbs up or not. So that took a long time to do the runs. Often took a long time to get someone who's the expert's time to do that. It was subjective. It wasn't good. I mean, we needed something that, the people developing the code and stuff could do. So we needed an automated tool. And so that's really going to be the thrust of this talk, is discussing kind of the automated tool that we came up with and like where we're going with it now and what it's been useful for. So we call it the Ensemble Consistency Test. So instead of trying to answer the question, is this a correct answer, or is this correct, somehow correct, we say, well, is the new data from Summit, is it statistically distinguishable from the data on the NCAR machine? And so asking this question really makes a lot of sense. I don't know how much people are into weather or weather forecasts, but these are nonlinear chaotic systems. So if you change just the littlest bit in the initial condition along the way, you can get a wildly different answer. So this is just kind of a picture of that, where they want to look at precipitation, and maybe they run 20 different model runs because they're not quite sure of the initial conditions. And they get 20 outputs, and then they sort of average them and say, well, here's your probability of precipitation. So thinking about climate or weather model in terms of an ensemble is really what they do in practice, because that's why you see a hurricane coming in and they're like, well, it's probably going to go this way, but it might go this way, but 80% this way. They've run a whole collection of simulations. So we decided we're going to run a collection of simulations, and that's the baseline on our machine, for example. And then we're going to somehow quantify the variability. And now when we port to a new machine, or we upgrade the compiler, or someone makes an optimization, we'll just compare it against that. So that's basically what we did here with this ensemble consistency test. And it's an automated Python tool. It's super easy. The CESM software engineers do most of the work because they make these ensembles that go with a specific tag of CSM, a release tag. And then the new user who's just wants to test out something they did just does a couple runs and can do this test. So just a little bit more detail. So we use the 1 degree model because it's not quite as expensive. The perturbations we make to create the ensemble spread are basically an order double precision perturbation to the initial temperature. And we have over 100 variables that we're looking at. We run the simulations for a year. And then somehow, when we run the same thing on the new machine, we need to figure out how to compare that. So you might think, well, I'll look at the temperature on the new one and the temperature on the old one, or I'll compare the variables. Well, that turns out to be hard because there are often hundreds of variables that are output, and a lot of them are really highly correlated. Like they might output temperature and surface temperature and max temperature and min temperature. And so, like if temperature fails, like 20 things just failed because they're all the same thing. But that's another issue with outputting too much data, which is a whole nother talk. Anyway, so what we needed to do was something a little smarter. So we used principal component analysis. And I assume most of you are familiar with that, maybe. The idea is that instead of being in this space of variables where everything is really correlated, we're going to project the data into this orthogonal space where now things aren't correlated. And principal component analysis in particular works to where you're always orthogonalizing in the direction of maximum variability, and then you orthogonalize against that and so forth. And so what we use for our test then is instead of looking at a distribution of the variables across the ensemble, we're looking at the distribution of these scores, which is the weight of the principal components. And the good thing is that we don't have to use all the variables, because I have this little chart up here. You may not really be able to read it. But the idea is that the most variability is represented by the first several principal components. So the end ones are really kind of noise, and we can just not worry about them. So even if we have, hundreds of variables, we can just look at, like, say, 50 principal components. A more statistical way to think about this is that we're really doing a hypothesis test, where our null hypothesis is, do the new simulations on the new machine come from the same distribution as the one on the NCAR machine? And so we're looking to see if we can reject the null hypothesis or not. So basically, the test is issuing a pass or a fail. And one thing we worry about that I'm going to talk about later is the false positive rate. And the false positive rate means we've said it fails, but really it shouldn't. And so we don't want that to happen. So I'll get into that a little bit more at the end. But so how does this work? So we did loads of testing because, of course, we had to make the case that they should stop doing the 400-year runs and that they should use this instead. And so we did lots of things where we changed the CO2 levels, or we changed the humidity, or changed something that we knew should be climate changing. And we made sure the test picked it up. And then I think a harder thing to do was to think of things that shouldn't be climate changing and make sure those passed. So even if you just change the order of operations on one line of code out of 2 million and you run it and it gets executed, you get a different answer. But I would certainly hope that's not going to result in a different climate. Or if we upgrade from Intel 15.3 to 15.4, I really don't want to get a different answer. So there's kind of a whole class of things there that you don't want to give you a different answer. And so this is used to verify these ports to other machines. We've used it to find errors in some of the component models. We found compiler errors. We found a random number generator error. And overall, it's been really useful. But of course, whenever you have something useful, the next thing you do when you're a researcher is think of how it could be even more useful or cheaper. So we started wondering, well, we're doing these year-long simulations. They're not that expensive, but it's kind of a lot. And we wondered, well, do we really have to run out for a whole year before we look at the variability and compare things? So we thought, if we went shorter, it could be a lot cheaper, and then we could make our ensembles a lot bigger. Things would be more stable. So we decided to just go the opposite. Well, I don't know what the opposite of 1 year is, but like 0 time steps. But just like how few time steps can we go? Like the limbo. How low can you go? We want to make sure we get enough spread that we can compare things again, but we don't want to get so much that everything passes. And the initial perturbations in these chaotic models, like the climate, go fast. So this is a picture that Dan Milroy made, and you can't read any of the words, but these are just a bunch of variable names with acronyms that are not at all intuitive. And the colors mean that as you go across a time step, I've got 0 to 10, the darker the color, the fewer significant digits are in common. So if it's like bright red, then that means like out of the double precision number has 1 bit that's the same. So you can see that right out of the cages, everything's changing. And stuff is even happening before time step 0, which is a little confusing, but there's initialization stuff. But this is a closer look at 3 variables, and you can see I have the time step here, and this is the difference between the unperturbed case and then 30 that we perturbed, again, just by the initial temperature, by something double precision, and you can see that it starts to spread. And really by 9 time steps, which is the first box plot guy, we were thinking, we think we have enough already, so let's try it, right? This is research. It's just someone's PhD thesis, right? They don't care if they graduate. So let's try it. That was a joke. Anyway, 9 time steps was like 70 times cheaper than what we were doing before. And we also weren't averaging it. And honestly, Dorit and I did not think that this was going to work. We thought we're just going to try this out. And it worked amazingly well. And we were thrilled. Doing the year-long tests and the 9 time steps, they were almost always in agreement. Anyway, it was very exciting. This is the excitement in my life these days. This was very exciting. And we were able to pick up compiler changes, basically everything we could do with the 1 year, we could do with this one. Lots of tests. And we tried to find counterexamples, like when would it fail? And to do that, we had to get really contrived. Like one thing we did is change the coefficient of how fast water drains through the soil and made it like 10,000 times faster. But you couldn't pick that up in 9 time steps because that was happening in the land model, and by the time it got to the surface and affected the fluxes and went into the atmosphere model, you were past 9 time steps. 9 time steps, by the way, is about 5 hours because the time steps they're 30-minute time steps. So in 5 hours, you can't make the soil water chain affect the atmosphere, in case you were wondering about that. This example is a little interesting, and I'm going to talk about it more later. So another thing we did is we realized that we probably could pick up smaller scale behavior at the 9 time step because we weren't averaging over the year. So we changed the random number generator that's in the cloud code. That's kind of like, we have a cloud. No, we don't. That sort of thing. So when we look after 9 time steps, it could see that the random number generator was different because it was the instantaneous value, and maybe there was a cloud and there wasn't. But after a year, that behavior sort of averages out, right? You wouldn't want your climate model to give you a different answer because you changed the random number generator. That's going to get you hauled in front of some committee in Congress. So anyway, so there were cases, but overall, this being able to use just 9 time steps made a big difference, and it was the reason that we could do the rest of the work we talked about, because now it was super cheap to run the model, and we can make as big an ensemble as we wanted, basically. So just kind of to finish off this section, this ensemble test, it really has been great for when you can't do bit-for-bit reproducibility. And it's really easy to use. And people who are optimizing codes that are great at that but don't really want to look at what climate data can see, oh, this is right, this is wrong. So anyway, so this was kind of a big deal. I forgot I put this in here. So I've been talking about the atmosphere all along. We also have a module for the ocean, which I won't really go into, but the ocean works differently from the atmosphere in that there are fewer variables that we had to look at. And this is just kind of the standard deviation of the sea surface temperature. And the variability is a lot different depending where you are. So we had to take a different approach for that. I'm not going to talk about that anymore. All right, so this next thing is something that, oh yes, sorry, go ahead.
Yeah, sorry, I had a technical question about the PCA.
Yeah.
When you do the comparison,
yeah.
are you just comparing the values, or are you also looking at the actual vectors?
So we are looking at the scores of the new one against the distribution of scores from the baseline one, and then we have we can specify the confidence interval and things like that, and how many can fail and That's how how we get the false positive. We basically have everything set so we get a 0.5% false positive rate. So, and I'm going to talk about that a little bit more later too. Okay, so we were all excited, like, oh yeah, we got this method, you run it, it says, oh, you pass, you fail. And then, right away, we run it on a machine actually at Argonne Mira, and it fails. And so they're like, oh yeah, this is really great. All right, why'd it fail? Well, principal components 4, 15, 7, 8, all failed. They're like, okay, well, what the heck does that mean? So basically the next logical step was, okay, we have to actually give some useful information when we say it fails, or they're going to be like, yeah. So this was a big part of Dan's thesis, is we get a fail, and now we want some tool that says, okay, go look at this module, or wouldn't that be cool, this line of code, or, because we got a lot of lines of code here. So, and this was motivated by one of the first things we did was test out all the CSM supported machines, and they all passed except for Mira at Argonne. We're like, why did this fail? So I'll spare you the details, but this was multiple months of my life that I'll never get back. And many climate scientists and computer scientists, and eventually we figured out if we turned the FMA optimization off, they are the same. So we wanted it, so there's another part of that's why is the FMA make that difference? But that's a whole nother thing. But the problem is the code is so big and complicated that it's how the heck do we figure these things out? So the idea with the new tool was that, somehow we're going to figure out, even though our test is in principal component space, we're going to figure out which variables were the most affected, and then somehow we're going to trace those through the source code, and we're going to figure out the important locations, and we're going to instrument it, and it's going to tell us, what's wrong. So, right, no problem, good plan, right? So the first thing, identifying the affected variables. So now that we can just run 9 time steps, we basically make a whole ensemble of simulations that fail and that pass. And now we're trying to see, well, which variables are responsible for the differing behavior between that. So usually we do a logistic regression. Sometimes you can just look at the straight up distributions. It seems like a cool idea to just see what variables are different at the early time step, but as you saw with that red graph I showed, things just blow up so fast that's worked for 1 or 2 cases, but mostly it just doesn't work. So Dan Milroy spent a good part of his life working on how to do this. And the first thing we need to do, so we have these affected variables. We're like, okay, we got these 4 variables. We feel like they're the ones responsible for the fail. So how are we going to figure out, the path? So we need to make the CESM source code into a graph. Okay. So the first thing we do, because we have, roughly 2 million lines of code, is we try to get rid of all the code we don't need. So luckily, when I was saying in the beginning, there's different components, you can switch things out and you can use different grids. So luckily, when you choose your configuration, some of the modules don't even get compiled. So you can probably throw out at least 50% of the code. So now we're probably under 1 million lines, so that's better. Then you can do a code coverage tool to see, okay, for the particular setup I did, what code actually got executed. Then you can throw out some more code. And the next thing, and this was probably one of the hardest things, was building the abstract syntax tree. And I admit I did not know what that was till a few years ago, but it's basically a tree structure that has the syntax of your code. So if you have, A equals A plus B plus C, it's a little tree with, A and B and a plus, and it's what a compiler does. So the idea was that we take our code, we get these abstract syntax tree, and then we would make a directed graph, and then we could just follow through to our output variables. So we had all these module files that we hadn't thrown away. We used this 2 different parsers in Python to make basically an AST for each module. Then we had to combine all these ASTs into one metagraph. So it says toolbox of parsers. We had to do our own custom parser. Things had to be applied multiple times. This was kind of a big, a lot of work. But anyway, and then we got this cool graph, which is a big hot mess. And this one actually is just with connecting the CSM modules. The modules are the nodes, but actually our graph connects the variables. So it's much denser to that. And the idea was, okay, we know these affected variables. We know these 4 variables that we think cause the fail. So let's use the knowledge of those 4 variables to reduce the size of the graph. Because the whole game we're playing here is that we have 2 million lines of code. We're trying to get it smaller and smaller and smaller. So eventually we have something that a human could look at and work with. Or, there are a lot of tools out there that do this kind of thing on smaller bits of code. I mean, I go to these correctness workshops at SC and someone has this cool tool and I'm like, oh, what's the biggest code you run that on? Well, I did a matrix vector multiply. And I'm like, oh, okay, that's not gonna work for us, but it sounds cool. So anyway, and the problem I told you about earlier with changing the random number generator, that little blue blob over there is actually from that problem. That's the subgraph when we threw away some things. So we get this subgraph. This is for the random number generator. And basically we do this iterative procedure where we're trying to figure out paths from the internal variables to the affected output variables, like what the possible paths are. So we divide into communities. And in each community, we do a centrality measurement and figure out which nodes are the most important as far as having lots of connections. The idea then is that we would instrument the most important nodes, and then we relook with our variables and compare differences, and we prune it again. So this is an iterative thing that happens. And eventually, the idea is that we have a smaller graph. And the red dots are the problems. I know where the problems are because we made this problem up to know where the problems are. The orange dots are the ones we were supposed to instrument. And you can see that it'll feed in, and now we just have a much smaller bit of code to work with. And so I should say that, so this code is called Rwanda. This is kind of example of what happened. We started out with a configuration of 1.5 million lines of code. Then, the compiled, we got down to 800,000. The executed, we got down to 660,000. Then we got a directed graph with 1,000. And so we just keep getting smaller. And so the part in the yellow is not production code yet. The other part is, but this part we're still working on implementing it. So this is a simulated out the approach. And this is something that has been really interesting for me and has been pretty useful. And I hope, even though Dan left, I'm hoping we can continue this work. So another thing I'll touch on that I've been working on recently is really wanting to understand better how this ensemble consistency test works, how the principal component estimates are made, how it affects what the ensemble size is. Because that's something I totally didn't mention at all, is what size ensembles we were using. I said what length we were using, but I didn't say what size. And that really controls the cost. Someone has to generate all these, and if we say, can you please do 10,000, they're gonna say, forget it. So that's important. Originally what we did is we started with a size of 150 because they said, well, we're willing to run an ensemble of size 150 one-year runs because that'll take a fair bit of computation, but not too much. So we're willing to do that. So we chose some of our other parameters, so we got this false positive rate that we wanted. Then when we went to the shorter runs of just 9 time steps, we kept all the parameters the same, but we realized we had to make the ensemble bigger to get the same false positive rate. And like I mentioned before, I mean, in any statistical method, you're kind of trying to balance your false positive rate with the power of the method. I mean, ideally, the false positive rate is 0, right? You never fail something when it should pass. But it's completely trivial to make a test that has a false positive rate of 0 because you could just pass everything and then you learn nothing. So it's kind of like a balancing thing you do. And right, so let me go to this. So this is one thing we've been looking at. Okay, K is the ensemble size. So basically what we're doing here is we did an obscenely large number of runs, and we wanted to see how well our principal components estimates from our method matched up with the true ones from the whole ensemble. And we found this interesting thing. So I don't know if you remember, but I said, oh, we're only using the first 50 principal components, which was a bit arbitrary. But we found that we were like overestimating at one part and underestimating the other. And at a size 300, when we go to 1,000, which is really too large in practice, it gets better. The reason we did this is we were looking at which principal components failed, and we were finding that, why does principal component 30 fail so much more than 1, or what's going on? So we were looking at that and found that, okay, we're not estimating things as well as we could be. So this is definitely work in progress. We do not have this figured out. But one approach we looked at is called thresholding. So this is more written from a statistics point of view. So we have our ensemble, and the first thing we do is standardize the variables to kind of make them so we compare them. And the way we get the principal components is they're just the eigenvectors of the correlation matrix. So that's what I put in the red box. So there's this idea called thresholding, and when I saw it, I'm like, oh, that's just like, sparsification in IOU or something. So basically, it's taking all the really small entries in the correlation matrix and zeroing them out, and then doing the spectral decomposition. So this totally easy change to implement, and it actually made a really big difference. And we don't totally understand why yet. So this is, like I said, just something I've been working on recently. But this red line is the 0.5% false positive rate that we're trying to get. And you can see that the traditional way we did it, we had to get up to like 350 or 400 before as the ensemble size before we could get it. But when we implemented this thresholding, now we could get there much more with a much smaller ensemble size. So we don't totally understand what's going on, but we do know that obviously the estimates of the principal component are really dependent on the ensemble. Obviously, for this test, the ensemble is everything, right? It's the baseline to which you're comparing new stuff. So it's really important what's in it and how big it is, and because you're using it to make all these decisions. So we're trying to improve the PCA estimation, and we're looking at the scores and how they fail, and we're just overall trying to understand the effects of some of these parameters. From the beginning, we've been like, yeah, let's use 50 principal components, the first 50, and forget the rest. But we've never, checked that out. So, yeah, I think this is my last slide. So this whole effort that I've been working on with other people in my group is really about improving the quality assurance, making it more possible to have confidence in the code, and then also to help the CSM developers find errors when things go wrong. It's unbelievably difficult to find errors in a code like this. And so so we feel like we've got a good first start saying, yeah, we think there's a problem or we're not. And we've made good progress with this Rwanda tool. We actually have a collaboration now with people at the University of Utah, and they have this tool called FLIT, and it looks at smaller codes and compares like compiler optimizations or this and that, and says, oh, this line of code is different or this line is different. So the idea is that if we can narrow our code down, we can be like, here, take these 5 modules, put them through your tool, and so forth. Because I mean, I don't really want to be writing tools like that. That's not my thing. But anyway, and then also looking into just getting a better theoretical understanding of how this ECT works, because ideally, you know, we want it to be as cheap as possible. And I think, yeah, we have a number of papers on things I talked about. I know I didn't go into a lot of details because I was hoping people would stay awake. But if you're more interested, you can contact me, ask questions. We have a lot of papers, and that's it.
We got some time for questions.
Yeah.
I'm curious, so this is for sort of comparing 2 implementations of what you think of as the same code.
Right.
Right?
Yeah.
What kind of stuff do you do just to see, even for one implementation, like, is this code correct? Right? I mean, I assume there's some standard stuff, but this is like big and complicated.
There's not really a simple answer because all the component groups sort of do their own thing, but they all have unit testing. They all have a suite of tests, things they all do. The part that's really hard is when all the components come together through the coupler and everyone's like, well, we only made 20 changes to our code, and so all 10 components made 20 changes, and we throw it all together, and now the Labrador Sea is frozen all year, and they can't figure out why, and that's a true story. That actually happened last year. So, yeah, so
Code or in real life?
in the code. Yeah, with the new release of CSM, there were many months trying to figure out why the Labrador Sea, which is the sea like way up in Canada. I've learned so much geography really at NCAR. I guess if I work there 20 years, I'm going to get some big atlas or something. Anyhow, yeah, it's complicated because there are so many people, and each code group, they all kind of like want to maintain control, but they all have their own testing suites as well. So, you know, regression tests, unit tests, yeah. So, yeah.
Are the random number generators only used with like the initial parameterizations, or are they used like continuously throughout the simulation?
Continuously. Yeah. Yeah. A lot of the parameterizations. And again, by that I mean a lot of the approximations for processes that occur at a smaller scale than the grid. A lot of those are extremely sensitive. And they, you know, like if you go above this tiny number, then do one thing. Otherwise, they're just really sensitive codes, and that cause a lot of the problems. Yeah.
Krista, quick question. You said something about 70 times cheaper. I thought the 5-hour model versus the year-long model. So is there some stuff that doesn't?
Yeah, the initial is it because there's like a chunk of time to even get to time step 0. So the initialization time,
okay.
Right? Yeah, is pretty significant.
And then, do the scientists, do all the scientists or critics buy into this, or are there people that are still like really nervous that like, oh, I'm sorry, you got to run it on our machine because I really don't trust those, you know?
Yeah. So mostly.
Yeah.
Definitely for the past several years, this has been the way we verify new machine ports. Just this morning, they're putting it on the Frontera machine at University of Texas, and they want to verify their port, so they're going to use our tool to verify their port. They want to do a high-resolution run, which means it'll be more expensive, but you know, so it's actively being used. It's also, so a lot of the other people in my group work on code optimizations, and they will sometimes use it too to make sure. Like one thing I worked on recently is we wanted to see if we could do one of the parameterizations in all single precision instead of double precision. And so when we changed that, we ran the test to see if it worked. And of course it failed. And so now we're like kind of being like, well, this part's a problem, but this part's good. And yeah, so that's like kind of why we want to get these graph tools working better, is to figure out, okay, which, obviously some part of the code is kind of unstable. So what's the problem? And that's the issue with this fuse, multiply, add too, is that, I don't have a problem against the fuse, multiply, add. In some ways it's supposed to be more accurate, right? But it kind of depends what you're doing. And there's probably just parts of the code that when you do that, it's just too sensitive or unstable and it's blowing up. And we found a few lines of code that do that. But it's like riddled through the whole thing. You can't just turn the compiler off one module and it works. It's, yeah, anyway. That's like the holy grail if we can figure that out. Yeah.
Is there some sense in which 9 time steps is optimal or better than say 8 or 11 or some other number?
Yeah, probably not. I did pick a multiple of 3 because there's subcycling going on, and so some variables aren't getting evaluated at non-multiples of 3. And but yeah, it worked, and since a 9 time step run is pretty much 99.9% initialization cost, it really matters very little if you did 6 or 9 or 20. It's pretty much in the noise. So, yeah.
So when you are, I guess, can anyone sort of verify against these NCAR runs, or the NCAR?
Yeah, so that's a good question, and the answer is no. We can't say running it without the FMA optimization is correct and running it with is incorrect. All we can say is that they're statistically distinguishable. And at some level, the climate scientists have to say well, okay, we don't care, or we do care. Like with the random number generator, we can pick out there's an issue, but it doesn't matter in the long term. One of the things I have started to do but haven't finished is run some of these tests out 100 years to see what matters on over what time lengths. But I just I did all the experiments but haven't analyzed the data. But yeah, no, it's really all we can do is say they're distinct or not. We can't comment on this one's more correct or this one. Unless, it blows up and crashes or something. When a code blows up and crashes, you can usually find the bug. That's the hard part about this, is we're looking in the output and saying there's a problem in the output. What's the problem in the code? Even though the code just ran fine. Yeah, I love it when my code just crashes and I can find out where it crashed. Cool. But if it doesn't, but it's wrong, that's when you're oh, yeah.
So when FMA was very first invented, the keepers of the floating point standard, in particular Bel Kahan at Berkeley, went kind of ballistic because FMA violates the floating point standard. And
right.
So here's sort of effects of that.
Right.
But so there's all different kinds of things that can cause failures. Do you have a sense for what the worst offenders are?
Not real. The kind of things we've run into, I could, we had the problem with the FMA. There was, I can't remember, I think it was Intel compiler 1503 or something, didn't work, and the 2 worked, and then 4 worked, and there was an actual bug in the compiler. There was some bug that only manifested on big endian machines, and I feel like that had to do with the random number generator, actually a bug, not just a different number. I don't. We had a failure because the ICE model, they did some upgrades and some initial condition was wrong. It was just wrong, and we were able to say, well, this failed, and they went back and like, well, the only thing that changed was the ice model, so it's this guy's fault, you know. So, yeah.
When it comes to those initializations, especially for all those different ensembles, how do you make sure that when you do the perturbations, even though they're that small, that since it's a chaotic system, it doesn't grow super exponentially very quickly?
It can. I mean, we just let it go. I mean, actually, I mean, there's lots of studies. I don't think I have any plots, but I mean, there's this recent study that they ran this high resolution climate model, CSM, from like 1920 to 2100, and they have 40 members, and people all over the community are studying it because it is amazing how much spread there is in, well, here, you know, the whole earth warms, and here it does. I mean, it's just a huge spread. So, I mean, the idea is that we're able to detect these errors that are so far, I mean, these errors are far enough outside the spread that's already there. Obviously, there's no way we could catch everything, and on the one hand, we don't have to, because if there is some bug, but it's so small that it looks like it looked by running the code on a different machine, then in a sense we don't care if there's a bug. So we're really just looking for, you know, egregious things.
That large ensemble study, by the way, is fascinating. So there's like 33-year trends, and there's example or members of the ensemble where like all of the 48 states get cooler, or where they like all get warmer by 3 degrees. It's an amazing spread based only on a perturbation of 10 to the minus 14 in temperature back in 1920.
And you will never believe another weather forecast or climate outlook again. No, but it's, yeah, that's why they always want to make the ensembles as big as possible, and we're trying to go as cheap as possible because, yeah, it's just, yeah, it's great. I mean, I feel like that plot I showed that Dan made with the colors, I mean, a couple time steps and there's no significant digits in common anymore. So it's, yeah.
All right. Allison's going to be available after this, and so I know a number of people are going to meet with her, and so if you want to join that, feel free to hang around. And with that, let's thank her.